It's November 7th, Election Day in Cambridge, Massachusetts, and welcome to the Mathematical Picture Language Seminar. We're very pleased today to have Stephen Girvin. He's at Yale, at the Yale Quantum Institute, formerly had been at NIST, University of Indiana, as professor of physics and applied physics at Yale. He's going to tell us about adventures in phase space and many related things. So Steve, the floor is yours.
Thank you very much. It's a pleasure to be here. Oh, like that. There we go. Okay, great. So, yeah, it's a pleasure to be here, see friends, and make new friends. So I'm going to be talking about basically quantum control. How do you sculpt interesting and exotic states in electromagnetic oscillators with the help of auxiliary qubits. So what I'm going to tell you about is based on a massive work in progress manuscript that I'm doing with other people, many other people in the Co-Design Center for Quantum Advantage. And I'm hoping that it will be posted sometime in the near future, but with this many authors and this length, it's taking longer than I would like. But the idea is that we believe that an architecture that consists of many harmonic oscillators coupled together that can communicate with each other by beam splitters and have auxiliary qubits attached to them to grant you universal quantum control is a very interesting architecture for computation and for quantum simulation of physical models that contain bosons. And it's also very good for quantum error correction. So far, there are 3 experiments in which quantum error correction actually made the memory lifetime better than the longest lifetime of any of the quantum components in the memory. And all 3 of them use bosonic codes realized physically in terms of microwave photon states in superconducting resonators. And having bosons natively available in your hardware means that you can do quantum simulations of physical models efficiently, more efficiently than in a qubit-only system. So the system that we have, you can show, in principle, gives you universal control. And there are, my experimentalist colleagues frequently dream up sequences of gates, instructions, which are numerically optimized to do very complicated unitaries if they want, but they're completely non-intuitive and non-understandable. So I've been kind of on a quest to try to develop some intuition and kind of figure out how to make these instructions human readable.
Professor,
Yeah.
what do you mean by universal control?
So, well, I'll define that, but what it means is you should be able to make any unitary that you want by making turning knobs on the Hamiltonian, modifying various Hamiltonian terms as a function of time. I'll talk about control theory a little more in a minute.
So is this the same as universal quantum computation?
Yes, so quantum computation, universal quantum computation means being able to make an arbitrary unitary on some given initial state and then make appropriate measurements on the output. So it's essentially the same thing as universal computation. So I'm gonna learn how to create these arbitrary quantum states. And I'm gonna, as an illustration of doing it in a way that we can understand what's going on, I'm going to illustrate that with a simple thing, which is deterministic creation of an interesting non-Gaussian state, the Schrodinger cat state. Then we also need to learn not just how to control and make these states, but measure them and benchmark the processes that make them. And we know something about tomography. We know how to measure the Wigner function of these states, for example, and it works well experimentally. But right now, we don't understand how to do an analog of randomized benchmarking, which in qubit circuits, you do a bunch of Clifford gates, you find one more gate that inverts all of that, and you measure how close to the identity you get. There are reasons that because the unitary group isn't compact in the oscillator case, we don't really know how to do that. So that's an open problem I'll list at the end. So our oscillators are electromagnetic modes trapped in superconducting boxes with Qs of 100 million to tens of billions. And the coordinate, I'm a fan of using first quantization in quantum electrodynamics. So the coordinate of this harmonic oscillator is the electric field at some specified point, and the momentum is the magnetic field. And I can address this oscillator, I can think about it in the Fock basis, the photon number basis, or because there's a countable infinity of states, there's also a kind of position basis. And this is why people refer to this as continuous variable quantum information processing. And you can represent, I'm going to do a lot of pictures for you, since this is a picture seminar, of quasi-probability distributions of interesting states in phase space, where again, the position of the oscillator is the electric field, the momentum is the magnetic field. And I'll explain these pictures a little bit, but this is a quasi-probability distribution, the Wigner function, for a Fock state with exactly 4 photons in it. So to do state tomography, you need to know the density matrix. That's hard to do sort of directly in these electromagnetic oscillators, which are oscillating 5 to 10 billion times per second. But it turns out to be relatively easy to measure the Wigner function. You take the state, you displace it in phase space. You take a point at the point alpha, which is x plus IP. It's a complex number representing the position in phase space. And you displace that point to the origin, and then you find the expectation value of the photon number parity operator. And sometimes it's positive, sometimes it's negative, sometimes it's 0. And that turns out to be the Wigner function, which is a partial Fourier transform of the density matrix and contains exactly the same information. And because X and P, don't commute, you can't have a classical positive probability distribution. It has to be negative in the most general case. There's another object, which is a different Fourier transform of the density matrix, called the characteristic function. And it's particularly easy for us to evaluate also. So you have a state, you displace it in phase space by a distance alpha, that's this displacement operator, and then you take the overlap of the displaced state with the original state. It's a kind of autocorrelation function of the state, which you can imagine is related to Fourier transforms, and hence back to the density matrix. And this is, it's a little tricky to take the overlap of a state that's been displaced with the original state, so you have to do a controlled displacement and use space kickback to do that. But it's very straightforward for us to do and very natural with the instruction set that we have available. So I learned yesterday there quite a bit of expertise, at least in a subset of the audience in quantum optics. So I'm just going to kind of briefly talk about sort of how do I decide how complex states are that I'm going to make. And for qubits, of course, the simplest thing is a product state. Then I can generate states from Clifford operations. They have entanglement, but nevertheless, those processes are easy to simulate classically by looking at the evolution of stabilizers. And then you have states generated from non-Clifford gates, like the T-gate, and they contain this very terribly named thing, magic, in which, so if you have Clifford gates and standard basis measurements, you can't violate the Bell inequality. You need a 45-degree rotation to get to the point where Bell inequality is maximally violated. And that's given by this non-Clifford gate. There's an analog of this for oscillators. There are some subtleties like
the previous slide.
Yep.
People, I see a lot of talk about fermionic states or what is it called? LDPC states. Is that
low density parity check?
Yeah, what is that? Is that even more complex than the last one? Or
LDPC codes are error correcting codes which you can create with they're stabilizer codes. You can create them with Clifford circuits, and you can measure whether there are errors by measuring the values of stabilizers. So they're not
okay.
they don't have magic in them.
Yeah, I see. Well, maybe I'm referring to something.
But what's interesting is in quantum error correction, it's a game, it's a competition between you and the noise demon. The noise demon has universal computational power, can do non-Clifford gates, and you, let's say you can't or you don't want to, you can still win the game. It's pretty amazing. So, and it's because when you measure the stabilizers, you collapse away into a state of either there is an error or there isn't an error. You make it discrete. And you can win the game if you're fast enough. So there's an analogous classification of oscillator states. There's the vacuum state, which you can make with a refrigerator. There are Gaussian states that are made by evolution with quadratic Hamiltonians. They're analogous to Clifford states in the sense that they're easy to simulate classically. You just track the mean and variance of the Gaussian wave packet. They're easy to sample from. And then there are non-Gaussian states, which are could be, for example, superpositions of Gaussian states, but not mixtures. Mixtures of Gaussian states are Gaussian superpositions, which can be made by Hamiltonians that are higher than quadratic, like if you have an x cubed term in your control toolbox. And the Wigner function now has negativity for these states, which prevents efficient classical simulation of various correlations, allows violation of Bell-like inequalities and universal computation. Okay. If there are questions, I'm happy to be interrupted. So this is a sort of big table summarizing these analogies between discrete variable and continuous variable, DV and CV systems. And I won't go through all the details, but this is taken from our paper, and I just put it here. If people want to look at it later when the slides are made available. But again, Clifford states have entanglement. I mean, they're quantum, but you can't do much, you can't do much with them relative to what you can do in a classical simulation. Okay, so again, since this is a picture seminar, I thought I would point out some of that if you use this phase-space quasi-probability representation, it's very useful to think even classically or semi-classically about the flow of a system through phase space. And we know that classically, the time evolution generates some volume preserving diffeomorphism in phase space, and Liouville's theorem says phase space is sort of incompressible. And in terms of the operator or the coordinates x and p, it's a symplectic transformation that preserves Poisson brackets or commutators in the quantum case. And so it turns out when you're trying to design some of these unitaries to do interesting transformations on your oscillator, it's useful often to think of these classical cases. So here's the squeezing Hamiltonian. Quantum mechanically, it's p hat x hat plus x hat p hat, just to make it Hermitian. But this is my favorite Hamiltonian when I teach sophomore mechanics. The equation, the Hamilton equations of motion for x, or x dot equals x, and p dot is minus p. So x gets big, p always goes exponentially to zero. That's the squeezing Hamiltonian, and it maps a circular region, which you could think of in the quantum case as the uncertainty blob, from a circle to an ellipse. If I change where now the momentum is becoming more certain and the position less certain, if I change the sign here, then I get the other squeezing where position gets squeezed and momentum is anti-squeezed. Here's a Hamiltonian that we like to call a cat amplifier. Suppose I had a Schrodinger cat state, which we're going to try to make later on. It's a superposition of a coherent state, displaced vacuum, which sits at some point alpha here in superposition with sitting at this point minus alpha. And because of damping, over time, the size of the cat will shrink. So suppose I want to make it bigger without distorting the shape of these coherent state blobs, then I want to have some, in a classical picture, an extremely uniform flow here with no a constant velocity so that the momentum is not changing. And here's a simple, if I could make this Hamiltonian tanh x p, then I would get something like that. And had an undergraduate who figured out how to make this work and do polynomial approximations of this. And you can just keep making your cat bigger and bigger to overcome one part of the dissipation. We also make quantum error correction codes out of four-legged cats that have a blob here, a blob here, a blob there, and a blob there in superposition. And you could use this to these flows to keep that cat alive. So I put these in partly just because they're pretty pictures, but we actually use these, it really helps with intuition when you're trying to design unitaries. Okay, all right, so now for a short course in quantum control theory. So control theory is you have some Hamiltonian and maybe it's zero in the interaction picture, but then you have some interaction picture perturbation, which is your set of controls that you can turn on and off as a function of time. So for a two-level qubit, I can, if I apply an electric field or magnetic field, whatever it couples to, I can excite it from the ground state to the excited state and vice versa with this Pauli X operator. And I can apply drives that will do that, that are a function of time. And I have two possible things I can do. I can apply cosine omega t or sine omega t. And in the frame rotating at the precession frequency of the qubit, which is pretty fast for us, it's 5 billion times a second. But with modern electronics, you can jump into that frame and not get dizzy. Then we have just this fast oscillation goes away, at least in a certain rotating wave approximation. And I can couple to Pauli X and Pauli Y in this rotating frame. So because it's precessing, if you wait a quarter cycle, right, X turns into Y, and these two pulses are quarter cycle, out of phase. So that's why you can couple separately Pauli X and Pauli Y. Okay. So there's a nice theorem that if you have a set of controls like this, and then that set of operators has a Lie algebra, and if the commutators of those generate the set of operators that's full rank, so you can make any they generate any unitary operation on your space, then you have complete quantum control. And for a qubit, there's some subtleties when you have oscillators and with an infinite number of degrees of freedom. And I will say here that there will be no epsilons and deltas or even any rigorous statements in this talk, but I think there's some open problems that mathematically oriented folks might be interested in taking a look at, which I'll summarize at the end. So the commutator of Pauli X and Y is YZ, and that's the complete, that gives you all the Pauli matrices. And so you can generate full SU2 rotations of your qubit using only these two controls. So you have universal control for a single qubit. So harmonic oscillator is not controlled. So a qubit is controllable with purely classical drives, two of them. That's not true for an oscillator because the thing you couple to, the electric field, in the rotating frame becomes the position and momentum of the oscillator, and their commutator is a C number, and the algebra closes, and you cannot do anything other than transformations that add C numbers to X and P. You can make coherent states, you can displace the vacuum, but you can't make Fox states, you can't make cat states, because the algebra is too simple. And physicists understand this because the uniform level spacing of the oscillator means that when you drive this transition, and you're trying to say Rabi flop it and just get one photon there, well, once it has amplitude here, this transition is also possible, it's the same frequency, and you always end up making a coherent state rather than what would happen in the qubit, where you could Rabi flop from here and back again. Okay, and that's the same, closely related to the fact that this algebra is too simple. Oops. Okay, so in order to fully control a harmonic oscillator with classical drives, we need something anharmonic. We need a qubit coupled to it. And so we're going to have our microwave resonator, which is a one mode of it, which is a harmonic oscillator. We're going to have a qubit here, a transmon, a superconducting qubit, and they will have a dipole coupling. There'll be a little bit of damping, but it turns out pretty small these days. This is the original Rabi Hamiltonian. By making some rotating wave approximation, you can get to this. And in a certain limit where the resonator and the transmon have different frequencies, you can make a Schrieffer-Wolff transformation and end up with this dispersive Hamiltonian. So this is the thing I'm going to work with. And this so-called dispersive coupling is extremely strong, vastly 3 orders of magnitude bigger than the damping.
So this is also in the rotating wave approximation.
There is a rotating wave approximation, and in some circumstances, you have to be careful about that. you also, our qubits aren't really two-level systems, and you have to take care of that. So in numerical simulations, we do a much more complicated thing for this. But for purposes of explaining what's going on, I'll stick to this. Does that help?
Yeah, so, I mean, in the older days, I think the idea was to just encode the data in the qubit. Now you're more
Right.
in the oscillator.
Right.
What's the advantage?
Oh, so, well, there are, lots of advantages. One is because the oscillator has a bigger Hilbert space than the qubit, it can replace several qubits. That's not a major advantage because, if I use the first n levels of the oscillator, I only need log n qubits to have the same Hilbert space dimension. So that's only a minor benefit. And in fact, you can't, if you try to replace 1,000 qubits with one oscillator, you need to have energies up to 2 to the 1,000. So that's not going to work. But for small numbers, it's actually quite advantageous. Then the other is just the oscillators can have lifetimes that are orders of magnitude longer than even the best qubits. So that's that.
Even though this qubit may not be that good, I mean, somehow that you gained.
Yeah, so these are the best state-of-the-art transmon qubits. They have half a millisecond lifetime, but you can make cavities with 30 milliseconds to 2 seconds.
No, but that's cavity on its own. Once it's coupled to qubit, it'll
Oh yeah, so then there's a control problem. How do I control these beautiful, pristine oscillators with my relatively bad transmons? And there's this inverse Purcell effect in which the cavity, once you couple in the qubit, its Q goes down because it's partly participates in the qubit. And so that's a challenge which we have to deal with. Okay. So it turns out that if you have this Hamiltonian, which basically says the frequency of the cavity, which is the coefficient of A dagger A, depends on the state of the qubit, or the frequency of the qubit, that is the coefficient of sigma z, depends on how many photons are in the cavity. So I can make operations which on the qubit condition on the state of the cavity, and operations on the cavity condition on the state of the qubit using this. So that's where the universal control is. So by turning on drives that couple both to the qubit and to the cavity, I can turn this interaction into this. So it's like a spin-dependent force, much like you have in an ion trap, where so here's a force, right, couples to position. Here's a thing that generates displacements, couples to momentum, and the sign of it depends on the state of the qubit. And because I can also do independently rotations on the qubit, I can make it conditioned on X or Y or anything I want. Okay. So now I have a richer algebraic structure because X and Y don't commute, although as they're commutators of C number, but now we also have the Pauli matrices. And so if I were to take little x, the position of the oscillator, coupled to big X, the Pauli matrix, its commutator with P at Y is our friend, the squeezing Hamiltonian, multiplied by Z. Okay, so it's a conditional squeezing. If Z is +1, it squeezes momentum. If Z is -1, it squeezes position. If it's in a superposition of +1 and -1, it does both. It entangles the squeeze state of the oscillator with the qubit. Okay. So I can keep going once I have that commutator, I can do another one, and you can see I can generate cubic polynomials and on and on and on. So the algebra doesn't close. And so in principle, I can generate arbitrary, at least polynomial valued Hamiltonians of arbitrary degree. So by using sequences of infinitesimal rotations appropriately arranged, I can do Trotter-Suzuki to add such interesting terms to the polynomial, or Baker-Campbell-Hausdorff to take commutators to raise the degree of the polynomial. And from that, in principle, generate a universal effective Hamiltonian for the combined oscillator qubit system, which has this form. There is some polynomial that acts only on the oscillator, and then a set of 3 polynomials coupled to x, y, and z that operate jointly on the oscillator and the qubit. That's the most general polynomial form of Hamiltonian for the combined system. Okay. Any questions about that?
So you can actually do this in the lab?
At some level, yes. So it's possible in principle, and some of it is possible in practice, which I'll show you. Okay, so our workhorse is going to be this, what I call the conditional displacement gate. You can give a momentum boost or a position boost or some arbitrary boost in phase space in arbitrary direction, conditioned on, let's say, physically it's always the Z power matrix, but because I have the ability to rotate it, if I want to condition on X, I just rotate X of the qubit into Z, do the displacement, rotate back. And then I have, these arbitrary rotations on the qubit around some axis on the equator of the black sphere, which I showed you before was sufficient for qubit control. And so I'll just make a circuit where I have qubit rotation, control displacement, qubit rotation, control displacement, just keep repeating that. And each of these instructions comes with parameters. How big is the displacement? How big is the rotation? And so I can do numerical optimization of this, not sort of at the pulse level where I figure out what microwave pulses I'm applying, but at this next layer up where I have parameterized instructions. And so here from Alec Eichbusch, who just defended his thesis last week, and Michel Deveray's group, he numerically optimizes these sequences to produce, for example, Fock states. So there's the phase space portrait. I think it's the Wigner function of Fock state 1, 2, 3, 4, and 5. And this is a very expressive gate set. It takes, only 4 to 10 circuit depth to make very, very high fidelity Fock states, for example. And how can you tell by looking at this picture that it's a Fock state? Well, from the number phase uncertainty. The number is completely certain. So the phase of the state has to be uncertain by 2 pi. That's why they have this sort of rotational symmetry in phase space. And then the number of sign changes you see goes up and up as I increase the, so red is positive. I guess this is actually the characteristic function. Red is positive and blue is negative. So the higher the Fock state, the more wiggles there are in the Hermite polynomials. And you just, this is data, by the way, it's not simulation.
So you put like 5 photons in the microwave cavity and it just stays there for
Well, it stays there for the lifetime of the cavity. So you have to do all of this in much less than a millisecond, but you have plenty of time to make all these things.
Yeah. So do people have some a relation between the complexity and the fidelity of this of making this fixed number?
Yeah, so this is, so here you see the infidelity, 1 minus the fidelity on a log plot. And of course, the greater the circuit depth, the more chance of errors. Most of the errors come from the controller, from the auxiliary qubit, which has a much shorter lifetime than the cavity. So this brings up this point that Sabir was asking, and The real challenge is to control these beautiful long-lived cavities with these not so beautiful controllers.
How do you like? What is the physical measurement that you like make to obtain plots like these? Like, how do you?
Yeah, so for the Wigner function, you just apply a classical pulse that shifts the oscillator in phase space. Let's say from this, I want the Wigner function at this point. I shift it to the origin, and then I measure the photon number parity.
I see.
And we have a trick for doing that, which I haven't explained, but it again uses this dispersive coupling. Sigma Z couples to A dagger A. So you can imagine if I just let that Hamiltonian evolve in time, if A dagger A is 0, the qubit doesn't precess. If it's 1, I can make it precess through pi. If it's 2, it goes through 2 pi.
Okay.
And it erases all the information about the photon number, leaving only the parity of that number. And it's a quantum non-demolition measurement. You can repeat it many times. It's an amazing capability, which is easy in circuit QED and not really possible in quantum optics.
So does that mean you can do measurement without disturbing the state of the cavity, kind of?
So people often misunderstand. The answer is yes, in a sense. Often misunderstand what quantum non-demolition means. So if I measure photon number with a photomultiplier, I destroy the photon, I eat it up, right? Here, we can use this dispersive coupling to cause the photon number to change the state of a qubit. I can measure the qubit, I can repeat this many times, it doesn't eat up the photon. But if I'm in a superposition, like a coherent state of 0 through 10 photons, and I measure that there are 3 photons, the state changes, it collapses to a Fock state of 3. But then if I measure it again, I get the same answer over and over. So the first measurement is random, all the rest are this repeatable. That's what qubit means.
Okay.
If I measured that the photon number was 3 correctly, but then my measurement apparatus, ate up the photons or changed 3 to 2, that would not be repeatable. That's not QED. Yeah.
So it collapses consistently onto a Fock state that you can repeat.
Well, it collapses onto an eigenstate of the operator you're measuring. In this case, the number. Yeah. So QED doesn't mean there's no collapse. But this is the characteristic function, not the Wigner function. We actually use a controlled displacement. So we do a superposition of not displacing the state when the qubit is in 0, and displacing the state when the qubit is in 1. And you can measure the overlap of those 2 states with 1-bit precision by measuring the qubit it puts out. It's an interference effect, and you average that many times and you get the characteristic. It's slightly easier than the Wigner function in some cases. Okay, here's some more states. You've heard of squeeze states. So here is the vacuum, and you can see the vacuum fluctuations in the electromagnetic field. That's a fuzzy blob, which has the right area. You might think, oh, vacuum fluctuations in a little microwave cavity with hardly any 0-point energy, they can't be very big. But actually, the electric field is uncertain by about a microvolt per centimeter, and it's very measurable with this technique. And if I turn on the squeezing, so here's 10 dB of squeezing. I reduced the variance in the X direction by more than a factor of 10, increased it in the P direction by more than a factor of 10, while preserving the area, getting very high fidelity. Here is a binomial code, which was a summer research project of a later Harvard grad student, Miles Michael. And this error correcting code has interesting looking quasi-probability distributions. And then here's the Gottesman-Kitaev-Preskill grid state code. It's sort of a Schrodinger cat in phase space, 35 different places at once. And this is holds the current world record for memory error correction gain and Michel Deveret's recent experiment. So this numerically optimized gate sequence is highly expressive, it's efficient, takes very few shallow depths to do all of this. But we have no, it's totally incomprehensible. If you look at all the particular circuit, why is it working? So we'd like to at least get a little intuition for how this control displacement instruction set works. So let's start by first calibrating the size of the control displacements. So here's space. And if I just take an oscillator in some arbitrary state, could be a thermal state, anything, doesn't matter. If I displace it around a loop in phase space, there's a constant Berry curvature, and I should pick up a Berry phase proportional to the area of that loop. So how can I, if I send a pulse down to displace it, how can I figure out how much it was displaced? Well, I can measure that Berry phase. So here's an experiment done in Michel Debray's group. You take the qubit, you apply Hadamard, so it's in a superposition of 0 and 1. And then using these control displacements, you take state 1 around a counterclockwise loop in phase space using these spin-dependent forces. You take, so the qubit is in 1, cavity goes in a counterclockwise loop. Qubit is in 0, cavity goes in a clockwise. So they pick up opposite Berry phase, but you end up back in the same state. So that just means that the qubit was rotated around the z-axis by an amount proportional to that area. And then you just do a Ramsey fringe measurement, and you do what every person interested in metrology wants to do, convert the thing you want to measure into a frequency. So as a function of the size of the displacement, you see these oscillations of the rotation of the qubit, and that calibrates for you the size of your displacements. Okay, so now I'm going to show you how to make a Schrodinger cat state using all these tricks in a way that's comprehensible. And it's a version of quantum signal processing. This is not the original paper, but it's a great tutorial paper from the Schwarz group that basically says that all the quantum algorithms are really can be understood using ideas that descend from the theory of robust control pulses in nuclear magnetic resonance. So roughly speaking, what quantum signal processing is. Suppose I give you a unitary. I know ahead of time that it's a rotation, let's say a 1 qubit around the z-axis, but I don't know how big the rotation is. And I want a circuit which uses, applies this unitary some number of times in some clever way, and create from this unitary a different one, which is e to the minus some specified function of theta sigma c. Now, why is that interesting? Well, if theta, I want to, let's say I'm doing NMR, I have a kilowatt amplifier that's sending down an RF pulse to make a magnetic field to tip the nuclear spins over. Well, a kilowatt amplifier is a kind of crude thing. It's very, very hard to get exact prevent gain fluctuations. So I have errors. I over and under rotate. I don't quite know what theta is. It's close to pi/2, but I can't quite control it. If I do this composite pulse, where I do 3 or 4 pulses, I can make it end up as a function of theta. That function is very close to exactly pi/2, independent of theta, as long as theta is near pi/2. That's the idea. That's what NMR people use. Okay. So how do I make a Schrodinger cat state? So I start, so again, I'm using first quantization for my electromagnetic oscillator. Here's the wave function of the vacuum as a function of position, not in space, but position here is the electric field, right? Center of the cavity. The qubit is pointing in the x direction, And now I'm going to apply a conditional or controlled displacement generated by the momentum operator. And I'm going to displace the vacuum to position alpha if the qubit is up, and to minus alpha if the qubit is down, because I have that z in my displacement operator. Okay. So that is a not a cat state, it's a cat, Schrodinger cat. You can think, you know, this is the cat is alive, and there's a healthy positive amplitude in the atmosphere, no poison. And cat is dead, and there's a very detrimental negative electric field in the cavity, which is somehow poisonous. Okay, so the qubit and the oscillator are entangled. The cat and the atmosphere are entangled. And my cat state is just a superposition of alpha and minus alpha, disentangled from the qubit. So my control task is to disentangle the qubit from the cavity and end up with the cavity in a superposition of two different places. Okay, how do I do that? Well, yeah, so I have to do something strange. I have to rotate the qubit by, let's say, minus pi over 2 if x is positive, and rotate the qubit by plus pi over 2 if x is negative. Well, how in the world did I possibly do that?
X.
But yeah, if I do that, then the qubit's pointing in the x direction, and it's disentangled. Okay. So curiously, you can use a conditional momentum boost to do this. So here's a conditional momentum boost. You apply a momentum plus k if the qubit is in the y state, and minus k if it's in the minus y state. Why is that going to work? Well, let's reinterpret this instead as a rotation of the qubit around the y-axis by an angle minus 2kx. It's conditioned on the state of the oscillator. Okay. Well, that's almost the right thing, because x, if I choose k to be pi over 4 alpha, then I will, if x is plus alpha, I get exactly the rotation I want. If x is minus alpha, I get exactly the rotation I want. It almost works. Unfortunately, there are quantum fluctuations in x because of the vacuum point. And so out here, I get a slight over rotation because x is bigger than it's supposed to be. And here, an under rotation because x is smaller. And the same thing on this side. But the rate of rotation, you know, k is pi over 4 alpha, it's getting small for large cats. So it's almost unentangled. Okay? And in fact, the fidelity to the exact thing I want is 1 minus pi squared over 64 alpha squared. Okay? It's pretty good. But still, it has this error. Is there some way to get rid of that? Well, here comes the quantum signal processing, or the NMR composite pulses. So when Paris invented something called the BB190 NMR pulse, which makes a pi over 2 rotation, even if the pulse you give it is slightly bigger or smaller than pi over 2. And it does it by 4 rotations, like this, and then 3 more, which cancel out to the identity if you gave it a pi over 2. And if you gave it slightly bigger than pi over 2, the next 3 cancel out that error to a very good approximation. Well, this was designed for classical fluctuations. How can I possibly use it to fix quantum fluctuations? Well, they're all in the operator x, which commutes with itself. And so you can elevate these NMR tricks, which fix classical noise, to now fix quantum noise. So here, so there's a sequence of pulses. There's the nominal pi over 2 rotation, but theta is only approximately pi over 2 because it depends on x. Then there are 3 more pulses, which is applying the unitary twice, 4 times, 2 times around with rotations around a particular axis of the qubit Bloch sphere. And if you choose these magic angles here, then I'm gonna plot sine of the actual rotation angle. And so red curve is sine of theta, and the blue curve is the sine of f of theta, the angle that I get with this composite sequence. And you can see it's extremely flat top, that it's very robust against errors in theta. It still produces a rotation very, very close to pi over 2. Okay. And these tricks have been known for many years in NMR, going back way even before Twin Paris. So if I do that, if I apply that with my quantum unitaries, where the noise is these fluctuations in x, I get to e to the I f of kx. And it very nearly, almost perfectly fixes the small under and over rotation. Okay. And then the infidelity drops by a couple of orders of magnitude in producing the state, and it's very nearly perfectly disentangled from the qubit. Yeah.
So this from your theory perspective, like you're not actually taking QSP, which is defined on like an SU2 space, like really generalizing it to like CD system. You're just using the fact that you have this dispersive coupling, doing QSP on qubit, and then you like transferring that modification essentially.
Essentially, right. But there's more to come. Okay, could we do even better? And the answer is yes. You can do non-abelian quantum signal processing, or maybe we should call it quantum signal processing, because so far all I've done is use unitaries that involve only the position of the oscillator to give momentum boosts. But I also have available the other operator, P. And now I can use the full power that P and X don't commute and the Pauli matrices don't commute to get to do a generalization of quantum signal processing. One of the I know one trick where I've understood how this works. I don't have a general theory of how to analytically figure out, construct circuits. That's an open problem I'll list at the end. But it turns out, so here's the state, right, with this little bit of residual entanglement due to the under and over rotation. So there's the coherent state, there's the residual over and under rotation of each piece. And I showed you with a NMR pulse, that's 4 pulses, some of which are big, like they're 4 times, they're 2 pi rotations, they're big. It worked, but it's kind of annoying to have to do all that. Instead, I can replace the entire sequence by a very small position shift here. And to first order, it fixes this. So why is that? Well, think about expanding this exponential, which has a small parameter, 1 over alpha, right? I get 1 plus something linear in x minus alpha or x plus alpha. And instead, since I know that these are Gaussians, I can get x minus alpha by just taking a derivative of the Gaussian, which is this p. And so that whole NMR sequence can be replaced by one very small conditional displacement about the y-axis. And it works extremely well, but to first order in these small fluctuations. So this is a hint that there's a potentially powerful generalization of quantum signal processing. And I wish I had a complete theory of this sort of non-abelian version of quantum signal processing. But these ideas, in fact, this last idea, which works for CAS, also works for the GKP code words, because there are sums of equally spaced Gaussians. And my postdoc, Baptiste Royer, used that to invent an autonomous error correcting scheme for the GKB, which was put in place in Michel's group and holds the current record for error correction gain. That's a whole separate 1 hour talk. So I'll just end with open questions. So I didn't talk much about benchmarking. I showed you that we can do tomography, but when in a qubit randomized benchmarking, you do a bunch of random Clifford circuits, and they do enough, they cover the block sphere well enough that you have a 2 design that it's a good approximation for measuring expectation values for certain operators, as it's as good as the Haar random measure. But the Gaussian states, you can have unbounded squeezing and unbounded displacements. And yes, you can follow what those Gaussian transformations do, because it's just changing the mean and variance. But we don't really understand, how to do an analog of randomized benchmarking. And then I skipped over, all the details of how you use these small rotations of Trotter and BCH. But because all the operators are unbounded, we need some mathematical help to figure out, can you really put bounds on the fidelity of say different circuit depths, how the fidelity converges as you increase the circuit depth. We don't have a really good idea of how to do that. And we don't have, except for this one simple example I showed you, we don't have a constructive theory of how to synthesize circuits using these gates. And so there's still, I think there are hints that this is going to be very useful, but we still have open questions. And here are some of the people that have thought about this with us. And we've got we've written an extension of the Qiskit language, which was built to describe qubits. We have a bosonic Qiskit that you can use the Qiskit language to make all of these gates if you want to do simulations, and it's available on GitHub if you want to play. And I'll stop there. Thank you.
Thank you very much, Steve. That was a really stimulating talk, full of beautiful new results and unsolved open problems.
And I hope some pretty pictures.
And many pretty pictures, yes. I'm sure that there is a great number of questions.
So for this, especially like the end of the talk, and I assume similar with the GKB states, a lot of these approximations work really well when alpha is large, or like you have a lot of photons in your state.
The one I showed you
Yeah.
required large alpha, yes.
But like experimentally, it's pretty difficult to reach like high photon states.
Right. So, but so in the experiment, they didn't use our analytically determined, well, they actually used that analytically determined thing. But in general, to create the GKB state, they used this just numerical search to find and use large displacements, not infinitesimal ones. And there you can get very quickly produce a nice GKB state with pretty high fidelity.
So you don't have to push, alphas like to really.
No, if you're willing to give up understanding how the circuit works, you can make it work fine. But I just get annoyed when the students say, "Oh, I found a numerical circuit that works great," and I say, "Why?" And they say, "I don't care, it works." And I just wanted to try to understand a little bit about why they work.
How do you couple like individual harmonic oscillators to one another? Like to intermediate it through qubit integration?
Yeah. Can I write on the board here?
Absolutely.
Let's see. Okay. So the way we couple, we'd like to produce some biquadratic coupling. beam splitter or two-mode squeezing, which produces entanglement. How do we do that? Well, we have a nonlinear element that sits here that has 3 or 4 wave mixing. It's a nonlinear thing. This has omega A, this has omega B, and I send in either 1 or 2 classical drives. There's some mixing that happens because of the nonlinearity, sort of in Feynman diagrams. It's phi to the 4th field theory, and let's say you can take a photon from cavity B, put it in cavity A, and make up the difference by transferring a pump photon from one pump to the other, and their frequency difference matches that frequency difference. And the nice thing about this is you can turn it on and off, and you can adjust the phase. And so you have very powerful controllable beam splitter by making the sum of these equal the sum of those frequencies. I can do two-mode squeezing.
I see. And experimentally, is this control, like, is it with high fidelity?
So yes, so we have a recent paper on a dual rail architecture where the 2 states are 0 and 1 photon, or 1 and 0 photons. That's a single qubit. And beam splitter is qubit rotations on the Bloch sphere. You can on some around the equator, which I showed gives you universal control. And the dominant error, the beam splitter is such high fidelity that you get about more than 3 nines of fidelity for the beam splitter operation. And if you post-select on the erasure error that you've lost a photon from these very high Q cavities that are much better than these other things, you get 4 nines.
I see.
And erasure errors would be very easy to correct in a next layer code because they have less entropy. You know where they happen, and so we're pretty excited about this as a architecture. So but you know, when we first did these in the last year, we've made 100x improvements in the fidelity of this.
I see.
20x in speed and 5x in this thing when you pump it, not heating up.
Yeah. Another question. What is the connectivity of this architecture?
Well, the simplest thing to do is have a grid of cavities and geometrically local near neighbor beam splitters, and then some auxiliary qubits. Other people have built sort of long distance buses or multimode cavities that can connect slightly more distant objects, say if you wanted to make an LDPC code or something. But because we have such high fidelity swaps, you can actually entangle qubits and cavities that are separated, you know, by 10 units, still have 2 nines of fidelities.
I see.
And we've recently written down how to synthesize, for example, Z2 lattice gauge theory, where you have Hamiltonian, which has A dagger B plus A B dagger, where there's a dynamical gauge field that determines the sign of the hopping of the bosons. And there's another term which couples in the Hamiltonian, which couples to X, that makes the gauge field dynamical. And it's all done using these types of gates that I've shown you. So we're hopeful that okay, this is, you know, it's 1 dimension and it's not that exciting from the lattice gauge theory point of view, but it's a start. I think this kind of hardware will be very interesting for those kinds of simulations.
Thank you.
Yeah, so will that possible in the future that this?
Sorry.
Yeah, will this be possible in the future that you can do like no billion things like before we mentioned?
Yeah,
today?
so this architecture, you could say it's sort of qubit, the traditional qubit based, and you use all of these to do remote entanglement and communication. There's simple gates for doing that, or it could be boson based and you use these for control, or it could be just, both. And yeah, it's extremely interesting, the stuff that has just been done in collaboration with folks here by Continuum. And in principle, this has so what's the difference between this and an ion trap? Well, in an ion trap, you have a sequence of spin qubits, and then you have a bunch of mechanical modes, and then each spin is coupled to all the mechanical modes. They all have different frequencies. There's 3n of them, and that can be a feature and it can be a bug. Here we have one qubit coupled to one bosonic mode. Okay, so that's very clean, no crosstalk. And then we have extremely good swap operations. So if I want to entangle this qubit with that one, instead of doing what the ion trap people do, I can do the same thing, but I have a very specific mode that I entangle my qubit with. Then I move that photon down here and do the inverse operation, just like in an ion trap, and I end up with these guys entangled.
Yeah.
And so we think the fact that we don't have each qubit coupled to all the modes, it's simpler. But it proves to be true. So we'll see.
Yeah. Yeah, and another question is like when you mentioned the bin splitter and you say this Feynman diagram, as I know from equation motion, like all the interaction are from the nonlinear terms.
Yes.
Yes, and do you actually introduce a nonlinear optics things in this?
Yes, this object is a kind of only weakly anharmonic qubit that has this has the cosine potential of the Josephson junction, and you expand the cosine to order 5⁴. Hopefully the rest are small, and you use that. It's a very weak anharmonicity with strong classical drives. That's the thing you want to do. And then you have to make various rotating wave approximations to pick out this term. But we figured out how to do it in a very clean way so that other undesired parametric processes don't happen, and it's very high fidelity. But it took a few years.
Are there any online questions?
Let's see in the chat.
I have another question.
Yeah.
Is it possible to use like this may be like kind of high level? Is this possible to use neutral atom qubits to use for the control qubits for the cavities?
There are ways to do really hybrid platforms where you have superconducting resonators and let's say nuclear spins or electron spins of controlled atoms. I think Andreas Wallraff has also done something in Rydberg, but I can't quite remember how that works. It's not the optical Rydberg transition. You have to do some microwave scale transition and then use a laser to affect the Rydberg. But these things have been tried. As soon as you have a laser near one of these cryogenic cavities, bad things can happen.
Okay.
As we know from optomechanics or things like Conrad Lehner's experiments, so it took him 10 years to figure out how to keep the laser from heating up the cryogenics, but it is possible. And you could imagine that ultimately, if we ever build a actually useful quantum processor, it may well be a hybrid combination of many different technologies, because you need short-term memory, long-term memory, fast gates, long storage. You know, the processor that's inside my computer is extremely heterogeneous, and you could imagine the same thing in quantum hardware if we ever get to that stage.
Thank you.
Either questions?
Yeah, I'd like to thank Steve again for coming up from Yale and giving an absolutely excellent. Good luck for the future.
Yes, well, we're having fun.